Okay, so what I will do today is introduce some geometric concepts. Let me start by saying that I normally use slides for this. It's the first time I will give it in the blackboard, and it's not that I cannot draw perfectly. I just want to not to put obstacles in your imagination. This is why my drawing is not perfect. Otherwise, so and. When I say geometry, I mean polyhedral geometry, and I will start by introducing every concept I will use, I think. We'll start from 0. The first one is that of a half space, right? So if we have a linear functional ax, smaller or equal alpha x, sorry, smaller or equal than beta, right? This is I will tend to have to use d for dimension, so the number of variables will be d. This defines a d-dimensional half space. So this is some well, in 2D, this is a line. It splits the space into parts, and we take one side. Okay? Just a small note. Of course, we can have if the inequality is strict, this is an open half space, which means we have this, but not the hyperplane itself. Okay. Now, if we take the intersection of finitely many half spaces, take this, dot, this. So now we have this object here, right? And this is called a polyhedron. So in general, polyhedra have flat faces, in the sense that, for example, a circle is not, because we cannot write it as the intersection of finitely many half spaces. That's obvious, but it will be relevant when we connect with partitions. Okay. I will go now to special types of polyhedra. The first one being a polytope. Yeah, so in general, I will draw things in 2 dimensions, right? Because that's what I can do. But whatever I say holds in any dimension. So a polytope is a bounded polyhedron. So for example, this is not a polytope, because here it's not bounded. But like this, or that, or, look, I'm drawing in 3D now. These are polytopes, right? So these are bounded polyhedra. And we have 2 representations of polyhedra, polytopes. So this one, so this definition is the intersection of finitely many half spaces. Okay? This is what we call the H representation. But an alternative definition for polytopes would be the convex hull of finitely many points. And that would be the vertex representation. Okay, so every polytope can be described as the intersection of finitely many half spaces or the convex hull of finitely many points. And what is a convex hull? I suppose we all know, but if I have a bunch of points, I take the smallest convex polytope that contains them all. Okay, so okay, good. Then we'll move to cone, which is
sorry, the V here. So the H is like half space, and V here is
vertex, but I didn't use the word. So I said points and not vertices because that's the two definitions later. So a cone is the intersection of finitely many linear half spaces and that means that they all go through the same point, and now I will have to draw in more than 2 dimensions because So these are cones, polyhedral cones. I will immediately break, so violate the definition I gave. So I will allow my cones not to go through 0. So this point, the apex of the cone, is not necessarily 0. I will allow translates of cones. So when I say cone, what I mean is the intersection of linear half spaces or translates of that. So, okay, now among cones, we have 2 important cases. So the first one is that of simplicial.
Sorry, what's the difference between a half space and a linear half space?
A what?
The difference between a half space and a linear half space.
B is beta is 0.
Beta 0, that's cool.
Yeah. I mean, I will never use this again. It's just somehow this is a definition, but yeah. Essentially what it means that the intersection of finitely many half spaces going through the same point. Yeah, so now, by the way, for cones, the V representation, here we had the convex hull, right? But it's also it is also the conic hull of the generators. Now, what are the generators? So here, for example, or these, for which I will give better names later, or I can do it now. These are called the extreme rays of the cone. So there are rays, and we can take the conic hull. Well, the conic hull is what you understand. We can write later about all the hulls and the differences. And these are the generators, right? So if we take this definition of a cone, this would be the V representation. So when I say V representation for cones, what I mean is the generators. Now, and since they are equivalent, I can, when I want to talk about polytopes or cones, I will either talk about the inequalities or I will talk about the generators. So a simplicial cone, a cone is simplicial if the generators are linearly independent. So let me draw a cone in 2D, and like every other cone in 2D, it is simplicial, right? Because there's no way not to have linearly independent generators in 2D. But in 3D, for example, this is not a simplicial cone, right? So we have 4 generators in 3 dimensions, not linearly independent. I mean, this would be a simplicial cone in 3D though. Okay. Simplicial cones are important. Now, another important case for cones is the unimodular cones. And it's okay, sir. A cone is unimodular if the determinant of its generator matrix is plus minus 1, where this is let's put them as columns. If we put the
So it just comes down to having the right number of generators, yes?
for simplicial?
No, for unimodular, because we can, once we hit a non-zero determinant, can we not play with the lengths of the vectors? Did I ask you two stupid questions?
No. Can we always?
Because the determinant's linear in rows, can you not get plus minus 1 using that property? Maybe?
I mean, let's see. What you mean is if I would take, so this is 3, right? Here you say if I would take this to be what? Like this?
1/3 and 1.
Yeah, right. Let me think about it. So the reason why I never thought about it is because I want my generators to be lattice points, the coordinates to be integer. But in general, I'm not sure. Yeah, it's possible. So yeah, this is the example for that. Or for a unimodular cone, you can take, for example, this. Or we can take also that, right? So, okay. So, good. Now, a supporting hyperplane, if I have a polytope or a polyhedron in general, so a supporting hyperplane is a hyperplane that touches but doesn't cut into my polytope. So for example, this is a supporting hyperplane, while this is not, right? This is also a supporting hyperplane. That's it. simple definition. Now, what is a face of a polyhedron? It is the intersection of supporting hyperplane with the polyhedron. So this, for example, is a face. This is a face, etc. Now, zero-dimensional faces are called vertices. One-dimensional are usually called edges, and minus one-dimensional are called facets. Okay, for n dimension. Good. Now, the last, I think, geometric definition I will need is the following. Let's say I have a polyhedron, and I pick a vertex, and I take the smallest cone that contains my polyhedron, and its apex is at this vertex. So, for example, here it would be that one. Now, you see, this cone is the smallest cone containing the polyhedron, having apex at this vertex. Or another vertex cone would be that one, right? Or if I want to show off and draw in 3D, it would be that one, right? So, okay. Good. How are we going to connect polyhedral to geometry to anything else we discussed this week? Well, the first thing I said was we started by a half space, which is defined by a linear functional. Okay. Then what is a polyhedron? Is the intersection, right, of a bunch of half spaces, of finitely many half spaces. So I have a linear system. Give me any linear system, this corresponds to a polyhedron, and any polyhedron is described in its H representation by a linear system. And so let's say an example. Let's say I have no. This is a linear system. Okay, I can also write it like this. It's a very small one because I want to have two variables because, as I said, I want to draw in 2D, right? So what is this one? It is this cone here, right? Okay. Now, if I have a polytope, what we will do is really take its intersection with the d-dimensional lattice. This is what we want to do, and we will call these points lattice points. So this is a set of lattice points in P. And yeah, so here I have this cone C defined by this system. Who wants to tell me what is this? Sorry?
Before that, you are writing x2 is greater than or equal to 0. I think that should be x1.
Then I just drew it in the wrong direction. Isn't correct? So the point is, this is x1 greater than x2, and x2 must be greater than 0. So x1, this is x1 being greater than 0 is implied, right? I think it's fine. Am I wrong? I think it's okay.
Which region did you want? Which part?
This.
Okay, can we think like that x1 behaves like x, x2 like y? Then for the first one, x is greater than or equal to y.
But so you see, so if I take x2 to be, So you see, no, I understand.
You are taking
The reason why I'm not sure I'm correct, because like you, we have the same problem, because I also like to think in V representation. What you're thinking, you're mixing V with H representation, okay? So these are different. The fact that we have two inequalities and two generators here is actually an accident. It's not necessarily the case. So, and it would have been if I could draw in higher dimensions. But yeah, so these two rays, they are not immediately visible in the system necessarily.
Yeah,
so, okay, what are these points here? Or let me make it a bit, so let's say, okay, obviously you cannot tell me what is 0 because it's way too many things, right? But let's say I take this here, and this is 5, right? Since you didn't answer the first question, I will raise and ask what is this? You really don't like to restrict the number of parts in your partitions, right? So this is just partitions in two parts, right? By definition. The only restriction I have when I have two parts is that the first part must be larger or equal to the second, right? And the second must be greater or equal than 0. So they are all positive. So these are partitions in two parts. The lattice points in here are partitions in two parts. And the lattice points in there are partitions of 5 into two parts.
Do you worry about the fact that x2 could possibly be 0? Do you worry about that?
Not at the moment. Because, I mean, 5 is a partition of 5 in two parts. Oh. Up to two parts. Okay, it's up to two parts.
Gotcha. Okay.
Actually, throughout the week, this will be our major problem. And I hope that by the end of the week, we will see what we can do a bit. In order to do geometry, we kind of need to fix the dimension we're working on in. And this, in general, means, I mean, we have to fix something. Usually, this is the number of parts, okay? Yeah. Or, if you say I want partitions of n, you can take n dimensions because you cannot have more than n parts. So, good. Now, we already have a promised connection to partitions. So, let me directly give two more examples. Because these are things that we can, I mean, fixing partitions in two parts sounds a bit ridiculous, right? But like plain partitions, nobody thinks they're silly, right? So, and for example, so what is a plain partition? You say that I have these four inequalities, right? So P1 is greater than P2, P2 greater than P4, P3 greater than P4, and P1 greater than P3. Now, this is my linear system. So, and it's perfectly reasonable that we fix the number of partitions. This obviously gives us a linear system. It falls in exactly what we are discussing. Or you can, a very natural, other natural thing is you say, I want partitions with parts from a specific set. Well, here I want the finite set, right? So maybe I want my parts to be from, I don't know, from this set, right? That's fine. In which case, we do have a slightly different perspective than the one we did here, because then what we do is actually, we ask how many of each part am I taking for my particular partition, right? So still, I want the sum of, okay. So I want the sum to be n. I want partitions of n. And how shall I call this? Not P, I assume, but let me call it A, right? So I'm saying I will take xi times part ai, and this have to sum up to n, right? So that's a partition of n with parts from this set. And then I also want every xi to be non-negative. And that's now my system describing partitions of n from this particular, with parts from this set. Okay. If you want me to draw, still I will have again just two parts. So, good. Questions?
Yeah, what is the intersection with square?
Sorry, with?
The intersection C and the square.
This one? Yeah. These are partitions of 5 into 2 parts.
Okay, but that can be any line?
Sorry?
That can be any line?
I mean, this one goes through 5. So if I say it goes through 0n, then...
I mean, for example, if the line is L is equal to x2 line.
Okay, so what... Okay, sorry. This line is the one telling me that this is a partition of n, right? So now I have partitions of 5, so it's this line. If I do a partition of 10, it will be that line. Okay? So this cone contains all partitions, and then we grade it essentially, right? So when you write the generating function, you have a bunch of monomials, but then you gather them usually according to the size, which is n, right? So that's exactly what we do here. We have all the monomials. Okay, let me clarify that connection. If you have so this is a multiplicative monoid. right? We can multiply two monomials and still be in the monoid, and x to the 0, which is 1, is the unit element of this monoid. And then we have this one, which is n to the d, and this is an additive monoid. And we can work with either of the two. I mean, they're isomorphic. So here is, if you like to write x's, here is if you don't. And if you have only vectors, then you can draw them and do geometry. So that's the point. But what was the question, and that was my answer?
Right, so in this case we have the... We have the...
It was about L.
So the answer here is 3, 2, 4, 1, and 5, 0, right? According to your...
Here?
The intersection, yes.
The intersection, I think it has only 1 point. How many partitions of 5 do you have into?
3 points. 3, 2, 4, 1, 5, 0.
Oh, yeah.
4, 1.
Yeah. Yeah, it should be.
So this can be generalized somehow too. So if you want partition into 3 parts, it would be set 3, and
Yeah.
you need another inequality somehow.
So actually, for any fixed d, it's not a problem. So there is no problem really. The thing is that if you really want to let n go to infinity, which is what most people in the room want, it gets complicated. So this is one of the things we're working on to work in arbitrary dimension, right? So arbitrary but fixed is fine. Give me any dimension you want, everything will work in the same way, etc. But if you don't say what the dimension is, you cannot really compute in this way. So yeah. Except if you have a lot of structure and you can do things, but yeah, so. Oh, yeah, right. So what do I write for distinct parts, since it was mentioned a couple of times today, right? So we said that this is again in 2 dimensions for 2 parts, but you can think in any dimension for d parts, right? So these are all the partitions into 2 parts. What happens if I want partitions in distinct parts? How does my cone look like? What do I change here? Sorry? It's that, right? Well, almost. I mean, here I would have a strict inequality, right? That's the difference, which means that my half space would be open. That's the only difference.
Because we have integers only, can we write x1 greater than or equal to x2 plus 1?
We can.
Do we lose any?
No. Because, so, okay, let's see what it is. So say that x1 is greater or equal to x2 plus 1. I mean, let me write this. So this is minus x1. How do I want to write it? Anyway, x1 minus x2 minus 1, right? Greater or equal to 0. where does this come now? I assume it's here. I think it should be there, because I know what the result should be. And then the other inequality is the same. I think we have that, which is the same thing, right? So, but that's very relevant. Okay, so the point is what we lost. So the old one was this, and the point is that in here there is no lattice point. Okay, so good. And of course, what we want is generating functions of lattice points in Polyhedra. Right? So now that we established already the connection of lattice points in polytopes with partitions, or compositions, obviously, then we want to move to the generating functions. Okay. By the way, something I will also do somehow differently than I think the rest of the speakers is that I like to keep things in the multivariate case. So I want to see the partitions rather than the number of partitions of something. Right? So here, I will not say 3, I will say these. And based on this bijection, essentially. So, okay. Let's start from the beginning. So the simplest thing we can do is take a simplicial cone. Let's compute the generating function of a simplicial cone. And this is my favorite simplicial cone. Yeah, this is simplicial, right? So yeah, I said that I'm not very good at drawing. I want more space. Okay, so how do we do this? Let's start. So here, this is 0, 0, right? So this is z1 to the 0, z2 to the 0, which is 1, right? I will take the first generator of my cone, and I will enumerate all the points it sees. So that's z1 to the 1, z2 to the 0, plus z1 square, plus z1 cube, etc. Right? I move in this direction. Now let me take the second generator once, and I will move to z1 3. So to 1 3, which is z1 times z2 cube. And with the first generator, I will move again, and this means I will have z1, z2 fourth. No. etc. I can take it once more, and I will move now to the point 2,6, right? Which is, I assume, here. And then I will use the first generator again, and I will have Z1 cube, Z2 6, and so on. Okay? Good.
In the second row, we have multiplication not plus. Z1 to 3, Z2 to 3, if one of that 3.
So which one?
Yeah.
Here, right. So,
Can you also check your drawing? I think you are going a little too far up.
yeah, but then this means right?
Good one.
So, okay, now let me tell you about generating functions and how I understand them, or what I will mean by generating function. So let's say we have a subset of z to the d, right? Now, phi a of z is the following sum. For every element of a, I take z to the alpha. And this is multi-index notation. Right? So this is a formal power series. I just sum the monomials z to the alpha, where alpha is an element of my set. And if there exists a rho, some rational function such that this phi a of z is a series expansion of rho, then this is the rational generating function of A. Okay? Now, why do I care about this? So that's a, okay, so if I write this thing, so this sum, I don't lose any information in comparison to what I have in A, right? But also I didn't gain anything, because if the generating function, according to Wilf, is just a closed line where we hang things, right, for display, and we didn't compress it in any way. If I have an infinite set here, if A is an infinite subset, this is an infinite series, I still cannot write it down, right? But this rational function may be way smaller. Here's an example. If I want to write, if my set is this crazy set, right? So that's an infinite set. I cannot even write it down. But I can very easily write down a rational function that represents every element in there, right? If I expand this by a geometric series expansion theorem, then what I get is it's 1, which in this way is exactly the generating function of my set, of the natural numbers, right? So, okay. So this is the good. And obviously this is a way, first of all, I can write it down, and it is way smaller than writing all these things, right? So that's what I want to do here as well now. I want to compute a rational generating function because that makes sense also computationally for what we're computing here in the cone. Anyone? So actually, this is my phi, right? It's phi of something, right?
Whatever 1 minus z1 times whatever.
Sorry?
Whatever 1 minus z1 times whatever 1 minus z2.
Exactly. So how do we do this? How did you do it?
I get it wrong. That's not what I said.
So okay. In the first row, so this is obviously that, right? In the second row, what we did, so we can pull out a Z1, Z2 cube. Is this wrong? No, no, it's not. So, and then what remains is 1 plus Z1 plus Z1 square, etc. Yeah. And here is the same. So this is Z1, Z2 cube square times this, right? And if I would continue, then in general I would get if I used k times the second generator, I would get this times this series. Which means I can pull out this from this sum. And what I get is, so this series we know that it is 1 minus this. And then I would get a sum of 1 plus this, which is again, by the way, I will not use any other expansion except for geometric series expansion. No? That's the only thing I need. Okay? So now.
Counting lines, horizontal lines, is that what this is doing?
So, yeah, so this one is going right, using the first generator, right? And then this one is taking the second generator. So if I use k times in general, this is if I use L times the first generator and k times the second generator, so k, so the second generator is 1, 3, so it's plus k, right? This is what I'm getting. These are the points. If I take L times 1, 0 and k times 1, 3, I will get these points. And if we decouple that, what we will get is yeah, actually this. And now it's clear how this is to the cube, right? Good. Perfect, or almost perfect, because what I want is the lattice points in my simplicial cone, which is not what we computed, right? So what we computed are points on this blue thing. So this is a semigroup generated by 1, 0, and 1, 3, but it's not the whole cone. For example, I don't have this point here. What do I do? Let me erase this. Well, let me just take this thing and move it here. What? Yeah, there. Right? So I just shifted. We have that the blue thing is this, right? Okay. Now for the green thing, it is essentially what we had before, but since every point we had, we shifted it by 1, 1, we just need to put we add 1, 1, right? In general, let me do it here. Right? So actually, I can do it here. How it would happen? So it's what we can do here is pull out Z1, Z2. And then what remains is exactly what we had before. Right? So this, the fact that we add 1 doesn't depend on K and L. So we just pull out the things we added and we have what we had. So it will be the same, right? It's just that it will be multiplied by Z1, Z2, right? Is this clear? And we are not done yet because we also have this point, for example, that is not covered. And what I will do is shift again, right? But I mean, now you know how this works. So this will not change anything except for the fact that I shifted by 1, 2. Okay? And now, this is the rational generating function for the lattice points in the cone 1, 0, 1, 3. If I expand this, I will get the lattice points in there. Okay, now observations. First one, what is this? It is 1 minus Z2, the generators, right? So let's say that G is the set of generators of my cone, right? The denominator is the product of 1 minus Z to the G, where G is overall the generators. What is the numerator then? You see, I like doing this on the board better than with the slides. Because my question is it in any way related, this 3 here, with the fact that we have 3 terms here in the numerator?
It's the area of the parallelogram, so it's numerator.
Actually, it's even stronger than that, yes. So here, I will take what we call the fundamental parallelepiped, which is the half-open, this half-open area. And this has 3 lattice points inside. Remember, here is open. And what are these 3 lattice points? By construction, it's easy to see that it is exactly the numerator, right? And the fact that we have 3 is not unrelated to the fact that this determinant is 3, because that's exactly the determinant of the generator matrix tells you how many lattice points you have in the fundamental parallelepiped. You have to stop me. So let me give this theorem. In any dimension, whatever you like, just what we need is that the generators are linearly independent. Then the rational generating function of C is this. So this for fundamental parallelepiped. By the way, since this is bounded, this will be always a polynomial, obviously. It doesn't matter if I write a rational function or a formal power series, because these are both the same polynomial, right? So here we have a polynomial, and here we have this product over all generators, and that's the generating function for the lattice points in a simplicial cone. That's a very important step, but we have to eat.